Okay, so we've talked about solutions already. This just goes into significantly more depth. All right. So we haven't really defined formally what a solution is. Okay. Every solution, no exceptions, has two parts. It has a solvent and a solute. One solvent, one or more solutes. You can have 10 solutes, but you can only have one solvent. Solutions are not confined to liquids also. Solutions, you can have any two substances that are homogeneously defined, like vodka and water. The air we're breathing, nitrogen, carbon dioxide, carbon monoxide, nitrogen, it's a solution. Metals can be a solution. Most people don't think of metals being a solution. For example, if you have a gold ring on, the chances are you've got some copper mixed in with the gold to make it less soft. Gold is pretty soft and it wears rapidly. And at close to $2,000 an ounce, you don't want that wearing away. So they put gold in there, and that defines the carats. Or you have a 17 carat ring or do you have a 5 carat ring? Big difference in price, not a lot of difference in appearance, in my opinion. My wife had a degree in gemology, and she could, just by looking at it, could tell you approximately how pure the gold is, and she could tell you the chemistry of an emerald versus a was pretty wild. But anyway, so solutions, okay, two or more substances mixed homogeneously. In other words, you cannot tell one from the other. The one that's in the most, has the highest percentage, is called the solvent. Everything else is called solute. And you have to have at least one solute in the solvent. Okay, you can have 10 in there, but you have to have at least one. Otherwise, it's not a solution. Now, is oil and water a solution? Correct. Why? Yeah, exactly. They're heterogeneous. One, you can tell one from the other. Now, everything in science, particularly physical science, talks about talks about the quantitative aspect. Here's some examples of solutions. And the gaseous solutions you probably not thought of as a solution. The solid solutions you probably not have thought of them as solutions also. Brass, gold alloys, tin mixed in with copper forms various alloys. Okay, all right. Now, when we talk about the quantitative aspect, when we talk about the quantitative aspect of solutions, there are two factors that are always at play, and we've only talked about one so far. We've talked about enthalpy, which is having to do with heats, reactions, and all that stuff. There's also another quantity, and you've all heard of it, that's called entropy. Both those together determine how a reaction will go. Entropy is temperature dependent. Enthalpy is not. So that's why when you're mixing things together, the entropy part of the mixture can be changed by changing temperature. Now, let's see, good, it's not defined up there. Who can tell me what entropy is? Just kind of your own kind of definition. Yeah.
Everything trends towards disorder.
Yes, it's a measurement of disorder or a measurement of order. It depends on your perspective. Now, think about, go home and I want you to arrange your socks in your drawer, just like if you were at boot camp. So they're just perfectly aligned. And they do this at boot camp. It's crazy. Your Foot Locker at boot camp has to look like it's been ordered from some store. I mean, everything's like perfect. Your underwear has to be folded a certain way. Your socks have to be folded a certain way. They're perfect. Okay. By the end of the day, though, at my house, if my sock drawer is well organized, I open it up and it's no longer organized. And mostly it's kind of been tossed. Look at your trunk of your car. My point here is that entropy is a natural process. Things go from ordered to disordered naturally. So that's a process that drives reactions. If a reaction starts ordered and ends up being disordered, that's favorable, that's more stable. And the throw in temperature is going to make things more random faster because things are moving around. It's just like you're going back to the Foot Locker in boot camp. If your DI comes along and they do this kind of stuff all day long, kicks your locker, then he says, open it. You open it up and your socks are not all aligned. He'll yell at you for not having an organized Foot Locker. I mean, literally, they do crazy things just for this training concept they go through it. Has anyone been in the service in your? You've sort of been. Doesn't ROTC kind of run that way? Yeah, I mean, you understand what I mean by. And then you have to be nice to them at the same time. Let me give you another example. This has nothing to do with entropy though. On our final day during basic training, we all had this giant parade. Everyone was all spiffied up, with their shirts on and they're ironed, with a seam here and everything. And this is in Lackland Air Force Base in Texas in July. And so the DI is going down expecting the troops, like this. And a bird takes a dump and lands right here on my DI, right here. And he goes, he wasn't in front of me, he was next to my buddy over here. And he goes like this, he looks at it and then looks at everyone waiting for someone to laugh or anything. It was just like, what are the odds during a parade of all people that lands on your DI? I mean, it's crazy. Of course, back at the barracks, we all had a hearty laugh over that. Okay, so anyway, entropy is very real. It's one of the factors that can drive a reaction. Now, in 1B, we'll talk about spontaneity of a reaction. We'll talk about equilibrium, a lot of other concepts. So up to now, we've just talked about the change in potential energy, the delta H, enthalpy. Really, we need to talk about something called delta G instead. That's like Gibbs, G-I-B-B-S. And that includes both H and S, enthalpy and entropy together. And that's a more accurate way of determining the spontaneity of a reaction. Entropy is really important. And it's not talked about until you get into a reasonable chemistry class. Like my basic class, we don't talk about entropy at all. Everyone knows about it. Everyone's heard about it. We don't talk about it. Okay. So A and B. What's the difference between A and B? I'm sorry, what?
180. Yeah.
Sort of. What did you? Yeah, you can consider A more ordered than B in that they're not together. I'm sorry? Yeah. So the driving force here is to mix. And don't forget, molecules are moving, assuming where the temperature is above absolute zero, things are moving. And so the tendency is to go from here to here. That's the spontaneous process. Okay. That comes in play in terms like things like osmosis, hydration, dehydration. A lot of those concepts involve entropy. Okay. Good old intermolecular forces come into play big time when we're talking about solutions. You've got solvent-solvent interactions, solute-solute interactions, and then solvent-solute interactions. All three together make up the general IMF of that solution, which determines things like melting point, boiling point, whether there's a barrier on the surface for surface tension. All those come into play to determine that. So that looking at those combinations, we have solvent-solute interaction, IMF, versus solvent-solvent and solute-solute interactions. Okay. Now, if this one is more powerful than this one, solution forms. Okay. That's called a solvating force. Now, solvating force and that's in direct competition with a so the solvating force will pull things apart and get them into solution. The crystal lattice force will keep them together and they won't go into solution. So this is like the battle of the universe. Two forces, which is stronger? Okay. Okay, what do intermolecular forces do during when you mix two together? You've got solute attractive forces. Do they like one another? If they like one another, it's going to take more force to pull them apart. Okay. Now, when we get into, we've talked a lot about this already. Now, the heat of solution, when we mix two things together, okay, something's going to happen. Either they're going to mix well or not mix well. You're going to get heat being given off or heat required. Now, ammonium nitrate is usually present in a cold pack. So when you break open the ampule inside of a cold pack, what happens is things get cold. So heat is absorbed. A hot pack is just the opposite. You break open the ampule inside and things get warm. You've probably used one of those more than the other one. Up in Washington, when we go backcountry, we're always using, and you probably use hot packs a lot as well. Okay. Okay. Now, when you mix two things together, we have a salt crystal and we pour in some water around it. What does that look like? Okay, we've got, because sodium chloride is an ionic solid, that means it's what forms are ions within the solid. Okay, so how does the solvent break apart the crystal? And what happens is if you're in a polar solvent, you've got negative parts and positive parts. So the positive cation where that electronegative oxygen is being attracted to that sodium. Okay, so we have a solvent surrounding the solute ion. And this is in 3 dimensions. Okay, so what it's called is called a hydration sphere. And it's the first hydration sphere because around further out, you've got the same phenomenon happening at a weaker state. So that's the second hydration sphere. So you have first hydration sphere, second hydration sphere. And you got the same thing happening for the anion. So you got two separate hydration spheres going on. And this is, I should have drawn this as 2 containers. This is really 1 container. Let me modify that a little bit. So it's 1 container. So there's a salt crystal in water. You all know that water will dissolve the salt, okay? What if we put some sand in the water? Silicon oxide. What happens then? Huh? It won't dissolve, yeah, just by looking at it. You all know that you put sand in water and back, remember the lab where you have salt, sand, and magnetite, mix it up, solder, the salt dissolves, but not the sand. Why doesn't the sand dissolve? It's polar. Do the best version of that, it's polar. It's tetrahedral. Silicon is like carbon. So what are the two forces acting again? We have the solvating force and crystal lattice force. Which is stronger in this case? What?
Crystal lattice.
Crystal lattice force, because that's the force that keeps the crystal together. Now, when you have your cup of coffee and you put sugar in, and your coffee's cold, versus another cup that's hot and you put your sugar in, which dissolves quicker? Why do you think that is? It's the what? We have the solvating force, crystal lattice force. Now, crystal lattice force is the same on both of them, right? What's the difference between the two? The solvent is the same, but what else about the solvent? Temperature. So we can further refine this. Okay, so the solvating force is temperature dependent. The lattice force is not. So we can modify crystal lattice force by changing the temperature. So if we wanted to dissolve, we increase the temperature. If we want it not to dissolve, keep the temperature low, like when you're making rock candy, for example, you want the temperature low. It gradually builds up. Has anyone made fudge? Oh, okay.
Like the condensed milk,
The what?
like sweet condensed milk type one.
Yes, and you put a lot of sugar in there?
Yeah.
Okay, and is fudge good with grainy sugar when you're all done? You want it what?
It's good.
And why, what keeps it from, what makes it smooth versus grainy?
Plus sweet condensed milk.
If you make fudge from granulated sugar. When you add it in, mix it all up, warm it up, and you let it cool. You want it to cool fast. That's why when you go to a fudge shop, they have a big slab of marble that's cold, and they dump the mixture of your fudge down on that and spread it out. They want it to cool fast. That means small crystals. That means smooth, like gelato, really smooth. Rock candy, you let it cool down very, very, very slowly, and the crystals are big. So rapid cooling means smaller crystals. Slower cooling gives you bigger crystals, and that's using sweetened condensed milk. Gets around. It's hard to dissolve. Okay. Now, what I'd like to get into now is one, you need to understand big time this process of something dissolving. Okay. We're talking about liquid solutions now. Okay. Make sure you can describe it with diagrams, what's going on. You need to be comfortable with these two forces, what's going on here. Also knowing that the solvating force is temperature dependent. Okay. Okay, so we talked about already. And this is a nice diagram of what I did. Okay. When we get into the equilibrium part, we get into the quantitative part of solutions. Solutions This is like lab 5. How do we measure the strength of a solution? Now it involves our good old friend mole. And because solutions are contained as a liquid, we have to talk about the containment. So solutions are measured a number of different ways. Tomorrow's lab is going to involve a way of measurement slightly different than today. The normal way to measure concentration of a solution is okay. So moles of solute over liters solution. And that's an uppercase M. I usually make it boldface, underlined. Okay. This is called molarity. There's another measurement. Called molality. So there's molarity, molality. And these can be the same depending on the situation, or they can be different. This is the common one, and the liters of solution. Now, we talked about this before. If I have a liter of water and I dump in 10 grams of salt, 10 grams of salt, what is our final volume a liter? Slightly more. It's called Archimedes' principle. When you get in a bathtub, the water goes up. Archimedes' principle. Okay. When you put solid in a solution, in a solvent, the level goes up. So the molality doesn't change because the kilograms of solvent doesn't change. It remains the same. So they're slightly different. Now, when we talk about how solutions change physical properties, we use molality, not molarity. Like tomorrow's lab, you're using molality. Okay, so let's look at a bunch of examples using this. Okay. Okay. So how will we do that problem? This is a two-step problem, and we need to go back to the definition of molarity, moles per liter. And that's moles per 1 liter, by the way. Okay, so the first thing we need to do is convert 2 grams to moles. And sodium is what, 22.99, and chloride is 35.45. And we don't want per 3 liters, we want it per 1 liter. Okay. Now you can take this and stick it there if you want to do this in one step. Some people like multiple steps. Okay, does this make sense? Now this is a dry sodium hydroxide, sodium chloride, dry. So we have one process of calculating concentrations via a dry approach. The other is a wet approach. So let's do a few more of these dry ones. Does everyone understand this, what we're doing? Anyone have a question? Okay. So let's do one kind of backwards. Okay. So we've got 4.56 liters of a 3.21 molar solution. How many grams of sodium chloride are in there? Kind of a backward way of doing what we just did. Okay. So in a 3.21 molarity solution, that means that 3.21 moles per liter. But we don't have 1 liter, we have 4.56 liters. So let's find out how many moles we have in 4.56 liters. That's simply going to be multiplying by 456. Okay, now we know moles. And we just convert that to grams. Okay. This here is just a ratio of moles to liters. So that means this has to be the same ratio. That's why we set them equal. Once we know how many moles we have, we just convert to grams. Okay. Now these can either be a 2 or 1 step process. Some people like to think more multiple conceptual steps, which is fine either way. Very Any questions about this? Okay. Now let's step this up a little bit. Okay, so here we're adding two solutions together. And this will be our salt solution again. What's the resulting concentration? Okay. Okay, first of all, concentration, as you know, is moles per liter. Okay, if we take two solutions together, the combined volume is going to be the sum of the constituent volumes, right? Okay, so one is 1.2 liters, the other is 345 liters. So our new volume is what? Yeah, 467 liters. Now, what additional information do we need to solve this? What are the units of concentration? Moles and volume, right? Yours paraphrase. Moles and volume. Okay, we've got volume. How do we get moles over here? Combined moles. Well, we've got to determine the moles of each one and then add them together. So volume times so whenever you multiply molarity times volume, we'll end up with moles. So we have a volume, we have molarity, we can find moles. Okay. So the combined volumes are 467, the combined moles, 842. Everyone okay so far? Yeah. Which one? This one? That times that. Molarity times volume will give us moles. Okay, now we have okay, so we have moles per liter. We divide 842 by 467, we'll get moles per 1 liter. Or 1.80 molarity. And when you get into acids and bases, pH is related to concentration of hydrogen ions, H pluses. So all these solution calculations apply to acids and bases related to pH because it's just simply solution concentrations. Same thing. Only we're using pH instead of non-pH. Who knows what pH means? Yeah. What's the definition of pH?
No, it indicates how acidic or basic a substance is.
Right. Mathematically, it's the negative logarithm of the hydrogen ion concentration. In other words, I said hydrogen ion concentration. Negative log means it's used to working with really small numbers. Because pH values are usually numbered from 0 to about 12. Most of the time, your acids you're working with in your body are extremely low acidity. So pH works really well. For example, your stomach acidity is pH of 2. All right. So did this calculation make sense? Yeah. .6. Oh, I combined the liters of each one. Liters on the left plus liters on the right is 0. Yeah. Yeah, when you dump them together, this is 2 and this is 1. You dump them together, you have 3. Yeah. Okay. All right, so let's do yet another version of solutions. Another way of mixing solutions is to start with a concentrated solution and then dilute it. Okay. For example, when you buy commercial acids, you don't buy them already diluted. Most people sell them very concentrated. It's much more economical because you're not paying for water that way. And then when you get back to your lab, then you dilute them. Problem is you have to be careful on diluting them because you can't add too little or too much concentrated acid. So what would a problem look like? Okay, so we have concentrated acid. Let's just say it's hydrochloric acid. We take 567 milliliters, it's 1.2, and we add it to 345 liters of water. That's our final concentration. Now, I want you to remember that volume times concentration equals moles. So remember, concentration is moles per liter. All right. We can, there's two parts to this. One, we need to figure out the moles, and secondly, we need to figure out the volume. How do we figure out the volume? How do we figure out the volume? Taking this many milliliters, dumping it in this many liters of water. How do we figure the volume? Yeah, exactly. You're just going to add the small amount to the big amount. And we have to convert them both to liters so we can add them. This is kind of a special case. Let's change the, because we're going to end up with sig fig screwing things up here. Let's, okay. Oh boy, more spam. I get at least 2 or 3 of these a day. Okay, so let's take 195 milliliters. Okay, so our new volume is 165 liters. Now, the way I had it originally before, when you do the rules for significant figures, when you add, it would end up being the same volume, and it's really not. So, okay, so our new volume is 165. What about moles? How do we calculate that? How many moles of acid are here? Yeah. Yeah. Volume times molarity equals moles. Okay, so we have 0.235 over 165 liters. So dividing by 165 will get us moles per 1 liter. So your new concentration is going to be 1.42 moles per liter. Okay, so let's check to make sure this makes sense here. We're taking a concentration of 1.2 and diluting it, right? So what should our new concentration be relative to 1.2? Less, because we're diluting it. What is wrong with this answer? It's more. So something's wrong. Okay, so what went wrong? Okay, we knew our final volume is 165. Okay, our moles are going to be did I do that right? 1.2 times. All right, I can't figure out what went wrong. What? Well, there's only one source of moles. And which you were just adding it to plain old water. So our new volume is going to be this plus that. Did I add this right? Yeah, that's right. 5. These are moles. What did I do wrong, you guys? Yes, that's right. So it's 0.142. So now, does this make sense? We start with 1.2, mix it all together. Because we're diluting it, the concentration should go down, and it did. So I want you guys to look at stuff and say, is this a reasonable answer? Because if it's not, you did something wrong. It was a very simple mistake. I need to pay attention to my calculators, 10 to the minus 1. Okay. All right, so let's do a couple more of these. Kind of looking at it from a different perspective. Okay. Let's make that a little bigger. Okay. So 12 liters of a 2.45 molar solution of sodium chloride using a 9.34 concentrated solution. How would I do that? Okay.
We want to figure out the amount of liters that will give us that polarity.
Here's the liters. Think about the definition of concentration. It's moles per liter, right? Are you scratching your ear?
Did you convert like the volts, the polarity, and then add them together?
We're going to take the concentrated one and dilute it down, right? Okay. And we need to end up with 2.12 liters of the 2.45. This is what they do in the stock room every day. Yeah. And as usual, I didn't hear a word you're saying.
Is it like we kind of multiply the fraction?
Yeah, sort of. All right, let's go back to definition, fundamental definition of molarity. In fact, let's get more room here. Um,
Without
well, first of all, we need to figure out how many moles is in the final solution. And then we're going to take the moles of this and supply it to that. The first step is how many moles do we have in the final solution? Okay. That's going to be right. So this is the final solution. So we have 29.4 moles in our final solution. Okay. That means we have to supply 29.4 moles from the concentrated solution to dump in there. So MV again. Okay. And we don't know how many liters of the concentrated. We do know the moles per liter though. That's and that is going to equal to 29.4 moles. So now we solve for L. That'll tell us how many liters of the concentrated we need to put into the dilute. Because the moles are the same. You just have more solvent to dilute it. So we need 3.15 liters of the concentrated to equal the same amount of moles for the dilute and concentrated. Okay, so the question goes back to, how would I mix a solution? I'm not done yet. I haven't said how to mix it. How about we mix this solution? Yeah, yeah, exactly. We need a combined volume of, what was it? I forgot. The combined volume here is 12 liters. So of the 12 liters, 3.15 of it is the concentrated. Okay. So now we need to find out how much water we need to add to bring it up to 12 liters. So we need to add 8.85 liters of water to the 3.15 liters of concentrated solution. Okay. So that's a nice variety of solution problems you're going to be running into. Okay, you start with dry ingredients, you start with wet ingredients, mixed to a final concentration. You add them together. What's the final concentration? Those kind of problems. Okay, and I'll give you some worksheets to practice those as well. Okay, so that's what I wanted to cover today. Now, when you go over there, yesterday, I noticed Sue's class was in lecture, and when you guys were all gathered around, she poked her head out. Now, I don't know if she poked her head out because you guys were noisy, or I don't know. I just wanted to be sensitive to her. Okay, so if you notice a class that's in session, just keep the noise down, okay? All right, you guys over there.